Yeah, good evening, sir.
Yeah, so good evening all. So my name is Parth Joshi. So I am basically I'll be conducting these sessions for this course. So I'll just quickly tell you about myself. So I'm just sharing my screen. Just let me know whether you are able to see it. So are you able to see my screen?
Yes, sir. It's visible.
Yeah, thank you. And and I'm also sharing my video as well. So are you able to see me and hear me clearly?
Yes, sir.
Okay.
Yes, sir.
Yeah, sure. Thank you. Yeah, so welcome all. So I'll be basically conducting these weekly problem solving sessions for this course, which is modeling and simulation of dynamic systems. So I am basically a PhD student at IIT Bombay. So I'm currently pursuing my PhD in basically in the Department of Mechanical Engineering at IIT Bombay. So, so I did my undergraduate degree in mechanical engineering from BITS Pilani, Goa campus. Then I worked for around 1 year at SKF Bearings. So SKF is basically a leading manufacturer of ball bearings and other types of bearings. And I also did some internships at Tata Motors and again similarly at SKF Bearings also. Then I joined my master's program, so basically MTech in mechanical engineering with specialization in design. So I did my MTech at IIT Bombay, and then I worked for around 2.5 years at Eaton. So Eaton India Innovation Center, which is in Pune, and so I was mostly working on modeling and simulation of vehicle systems. So in both my masters as well as PhD as well as my industry experience, so I have been using MATLAB Simulink and other types of tools for modeling and simulation of different kinds of systems. So my main focus has been on automotive type of systems. So in my PhD, so then I joined my PhD program at IIT Bombay in January 2021, and so I have basically received the Prime Minister's Research Fellowship. And as a part of that, so I got this opportunity to interact with all of you to conduct these weekly sessions for these NPTEL Swayam courses. So welcome all. So before we get started, I would just like all of you to just quickly like introduce yourself. Like if you can just quickly share what which place like you belong to and which area, like are you if you are a student or whether you are a working professional, and like what is your general background so that I get an idea of what how to proceed further. So if you can just quickly tell about yourself, like yeah, yeah.
Good evening, sir. Myself, Maruti GV. I'm working as assistant professor at Global Academy of Technical Education, Bangalore, Karnataka.
Okay,
Basically, I worked as assistant professor in my previous. I worked as assistant professor in one engineering college for 7 years, and after that, I joined Autodesk company, and there I worked for 3 years. And after that,
okay,
recently I joined this Global Academy of Technology as again assistant professor, and I just registered PhD at Vishwesvaraya Tech University, Karnataka.
okay.
Thank you.
Sure. Thank you. So you are basically from Karnataka, right? Like, okay.
Yes, sir. I'm basically
Okay.
from Karnataka.
Okay. Great. Yeah. Thanks, Mr. Maruti. Uh, and so like, what was your motivation to join the course?
Sir, basically now I'm doing a PhD on bearing design and manufacturing. So I thought that this particular course will help me for my research. And also by learning this now we can uh, uh, train our students regarding building and manufacturing, sir. That is
Okay.
what that's why I joined this particular course.
Okay. Yeah. Good. Yeah. Good. Glad to know. Thank you. Anyone else?
Okay.
So
Welcome.
just wanted to know. So your background is mechanical engineering itself?
Yes, sir. My basically be from mechanical engineering only, and my completed my MTech from Vishweswara Technological University only. The college name is UBDT, Davangere, and in design background, sir. Machine design is what my stream.
Sure. Sure. Yeah. Okay. Thanks. Yeah. Good to know. Yes, Mr. Mohammed has raised his hand. So yeah, please. So if you wanted to speak something, yeah.
Yeah, hello. Good evening, sir.
Yeah. Good evening. Yes.
Yeah, this is Dr. Mohammad Mohtaram. I'm working in Global College of Engineering Technology in Oman. I
Okay.
came here in 2003.
Okay.
Earlier, I was working as a assistant professor in Waljad College, which was affiliated to Birla Institute of Technology, Ranchi.
I see.
So I came here in 2003. So here there is no scope actually of research.
I see.
So so I was just only teaching.
Okay.
So next semester we are actually hopeful to start a new program. There is a master program, and in which there is a module related to modeling.
I see.
So that's why I joined this course, so
Okay.
that I will get knowledge and then I will be able to teach.
Great.
And
Great.
basically, I am from Roorkee.
Rookie. Okay. And
Yeah.
you like your background is like mechanical engineering itself?
No, no, no. I am from electrical background.
Electrical. Okay. Fine. Okay.
Yeah.
Thanks. Thank you for sharing, sir. So you are from like you are joining all the way from Oman.
Yeah, yeah,
Okay. Okay. Okay.
yeah, yeah.
Sure. Thanks. Thanks for joining.
Thank you.
And I think yeah, Sukhman Deep Kaur. So can you just quickly tell about your background and like your motivation and all that?
Yes, good evening, sir.
Good evening. Yeah.
Sir, I am from Punjab and BTech third year mechanical student.
Okay. Okay.
And my motivation for joining this course was to learn and gain skills in modeling and simulation. So,
Okay. Great. So great. So are you doing this course like as a so you are like doing this course independently or like you will be doing this course as a part of your BTech
no,
curriculum
sir, independently.
independently? Okay. That's great. Yeah. I think nowadays
Yes,
we have the facility to, take the NPTEL credits and add it to your BTech curriculum. I
yes,
think you
sir.
can, yeah, right, sir. Is that correct? Yeah.
Yes, sir. It's called honors degree in
Right,
mechanical.
right. Yeah. Okay, great. Thanks.
Yes,
So, and your background is mechanical engineering?
yes, sir. Mechanical engineering.
Mechanical. Okay, fine. Sure. So we have like like people. So because this subject can be taken by anyone like from any discipline. So like when while teaching, then we need to kind of have some idea like what is like someone may be familiar with something and someone may not be. So then yeah, so then I can just adjust accordingly. Sure, thanks. So maybe we'll get started now with
Yes, sir. Actually, our hello.
yes, sir.
Sir, actually, the topic is that our university BT also introduced this NTL courses into our 8th semester curriculum, sir.
Mm-hmm.
So, if a student he want to complete 2 or 3 subjects will be in the 8th semester, sir. Instead of that, the student can go for NTPL courses. That is equal to one subject. It's a
Okay.
great thing.
Yeah. Okay. Okay. Yeah. Great. Sure. Yeah. Anyone else wanted to share anything else? So any comments, questions before we get started? So yeah, so let's get started. So basically, so I've made a list of what all are the general topics that will be covered as a part of this course. So, and this week's content basically deals with the first item itself, like the introduction to modeling and simulation. Then the method of modeling, which is called as bond graph modeling technique, will be covered. And then there are like we can actually generate some kind of template models for basic like mechanical systems, electrical or hydraulic kind of systems, and we can like it's like building a library of common component models which can we can use it frequently in our uh, modeling of a bigger system. And then we will be discussing about system models of combined systems where we combine both electrical or mechanical, so which is called as electromechanical or electro hydraulic or whatever those kind of systems. Then we'll be basically looking at the uh, dynamic response of different systems when they are subjected to, let us say, some kind of force or some initial conditions. So then we'll be basically discussing the concept of transfer function and the other techniques like block diagram and signal flow graph to represent this similar transfer function. Like so those are like the concepts which are borrowed from the control systems kind of courses. And then we'll be basically dealing with state space formulation, which is again another technique to kind of represent the like a model of a different system, which involves like multiple states, system states. Then we'll be looking at common frequency response like Bode plot and other kind of frequency response like so Nyquist plot, Bode plot, etc. So again, these are things which are generally part of like the control systems kind of courses. And we'll be mostly looking at using MATLAB Simulink as tools for modeling and simulation. So I have been using MATLAB Simulink for the past 9 years, and I have been extensively been using these tools for modeling of, like as I mentioned, vehicle systems. So yeah, and like I just wanted to mention that you can also use, so it's not necessary that you should always be using these MATLAB or Simulink kind of tools. So as a for this course purpose, we'll be sticking to MATLAB Simulink uh, because you will be having, I think, access to MATLAB for the duration of this course. So am I correct? So you will be having access to MATLAB, right, for this course?
Yes, yes.
So that's a good opportunity. So if you are already familiar with MATLAB, so how many of you are already familiar with MATLAB?
Yes, I am familiar.
You're okay. And anyone else has already used MATLAB earlier? Yeah, so it's okay. So I think we'll be discussing MATLAB, some examples in MATLAB Simulink as a part of this course. So this is a good tool which you can, and it's very powerful. It has a lot of functionalities. So you can use it to create different kind of system models. And then I think the last part of the course will be dealing with like more advanced techniques like system identification, parameter estimation, and optimization. So now this week's content is basically first of all introduction to modeling. What are the different examples of models like physical model or mathematical model or those kind of concepts have been covered. Then a brief introduction to modeling of dynamic systems. So like concepts like static or dynamic systems have been discussed. And then the definition of what exactly is the process of simulation that has been discussed. And basically the MATLAB has been introduced as a simulation tool as a part of this course. So what I plan to do now is to basically discuss some sample problems. So some of these problems are like very similar to the kind of problems you will be seeing, you'll be going through in your assignment, weekly assignments, and some of them are like more or less conceptual, like they will help you understand some of the concepts. So, so I have collected some problems, and also I plan to give you a demo of how you can use MATLAB for modeling and simulation. So I'll be just discussing a couple of examples of some sample problems which I thought of, and so that's what I'm planned for this particular session. So any questions or comments? So anyone has any questions or comments?
No, sir.
Yeah. So if you have any question or any doubt, like, so you can just unmute yourself and speak. So because I'll not be, because I'm sharing my screen and I would not be able to see the chat window as such. So it's better if you can just unmute and speak. So yeah, so we'll start with some sample problems. So the first problem is, so when a system or activity is probabilistic, so what it is called. So all of you can just, if you know the answer, so you can just tell me, like, what do you think would be the answer?
I suppose it is stochastic.
Yes, you're right. You're right. So stochastic is basically when there is some kind of random variation of uh, the particular properties of that system. So then that is called, that's why we call it as probabilistic. So yeah. So the next problem is, uh, so in dynamic systems, the interaction causes changes over which of these quantities?
Sir, time.
Time. Yeah, you're right. So, so by dynamic systems, we basically mean that there are things which change with time. So that's why we call them as dynamic. So the next question is, like, which model represents a system at a particular point in time when the system is in balance? So any idea?
I think dynamic model only.
It's actually static model. Why?
Okay.
Because so static. So what we call static is that when, let us say if there is some certain system which has like several forces acting on it, but the system, let us say it's in like equilibrium. So for example, you hang a mass from the roof with a spring, and you like allow it to stretch, let us say by some extent, but after some time it will basically settle down to a certain position, so it's in equilibrium. So there are forces like the weight and the spring force acting, but they are in balance, so that's called as the static condition. So a static model represents the system at a point when it is in balance. But yes, dynamic model can also be used, but it will basically not. So when we say it's in balance, so then the system will not change with time unless there is some external disturbance that is acting, which causes things to change with time. So for example, if so there is an example given in the lectures as well. So when an aircraft is actually flying in steady flight at a constant altitude, so then what are the forces acting on a lift, like on a aircraft which is flying like a steady flight at constant altitude? So any idea of which are the forces acting?
There is a force which up thrust force. There might be some up thrust force, and will be a force which will push the plane, and there will be a force which will turn the rotate, give some rotation.
Yeah, so basically like for a like let us say this line represents an aeroplane. So when it is uh, flying in a steady way, so then it's actually horizontal, flying in a horizontal way. So then there is a force acting which is basically the weight. So let us say W, and because of the wings and tails and all the body, etc. So there is a lift force which basically helps the aircraft to fly. So there is a lift force because of the air flowing past the wings, over the wings. So there is a lift that is being generated. So that is another force. Then the engines are providing the forward force for the aircraft. So that is called as thrust. So the engines will provide the thrust force for to propel the aircraft forward. And whenever like an object is moving through a fluid, because of the viscosity of the fluid, or basically the friction of the particles which are in contact with the body, and also because of the difference in pressure between the layers of the fluid that is being created, so there is a drag force that is uh, basically trying to resist the motion of that aircraft. So let us call it as D. So when the aircraft is flying at in a steady manner, so then uh, so all these four forces will be in equilibrium. So the lift force will be balanced by the weight, and the thrust will be just sufficient to overcome the drag. So this is like an example of a static condition. Although the aircraft is actually moving, but it is moving at constant speed. So as per whatever the Newton's first law, so we can basically say that it's in a state of uniform motion. So that's a kind of a static. It can be called as a static state. So does that make sense?
Yes, sir.
Yeah. So someone is trying to join. Yeah. So the next question is, it shows the steps in the design of a dynamic systems. So you have to identify the correct sequence of the different steps, how we go from basically the like a system to the final outcome of that like so you have to basically pick the correct order of the steps.
So second option is correct for this answer according to me.
Yes, you are right. So we will basically start with a physical system, and then we basically develop an engineering model of that system, and these things uh, which are basically mentioned above, like block diagrams or classical methods or bond graphs, or so basically they are different kind of techniques or representations of that model. And then we basically get differential equations. So we can convert basically these representations into differential equations which are function of time, and then we solve these differential equations using a computer. So that is basically the process of computer simulation. So that is the correct order. So the correct answer to this question is option 2. The next question is, an architect before constructing a building makes a scaled down model of the building which reflects all the rooms and outer design and all these features. So what kind of a model is this?
Is it a static physical model?
Yeah, you're
No,
right.
no, no,
So
sir. Correct.
yes, you're right. So it's a static physical model.
Hmm.
Uh, so it is physical because the architect has built a scaled down model of that building, which is actually a physical thing. And why it is static? Because like the building model, it's like generally not designed to move here and there. So that's why like, it's called static. So yeah, that's the correct answer. So which of these following is not a principle which is used in modeling?
Sir, I guess analysis is not used in modeling.
Yeah,
Relevance aggregation and block building used in modeling, but analysis is not used. So,
yes, you're correct. So analysis is done after you have the model. So you're right. So now next we have two statements. So you have to decide like which of these statements is true or false. So any idea which of these statements is true or false?
I think, as you earlier explained, statement B is correct.
Yes.
But for time varying, if stresses are there, so maybe B is also correct.
Yeah, so both are actually correct. So you're right.
Yeah.
Yes. So yeah, as we just discussed, so in steady flight, things are basically the forces won't change with time. So then we can use basically just a static analysis to calculate the stresses in the wings. But in the other phases of flight, so when let us say the aircraft is taking off or climbing or doing the descent or landing, or when it is flying through turbulent air, or other examples like emergency maneuvers or hard landing, etc. So then we will have things which are changing with time. So in those cases, we need to do a dynamic system analysis. Yeah, I think someone was trying to join. Yeah, so let's look at another example. So here we have like a block diagram representation. So we have like a set of input variables and output variables, let us say. So we have, let us say, the input variables are known, like we have several values of input variables and the corresponding values of output variables for a large like number of these input and output variable combinations for a certain dynamic systems. And our task is to find what is the model of that dynamic system for the particular state variables which we have chosen, let us say. So what is this process called?
This is called synthesis.
It's actually called identification. Synthesis is somewhat similar, but actually speaking, when you have to identify the dynamic system for that and the combination of that for that particular combination of state variables, that actually is called as identification. Synthesis is very similar. It looks similar to that, but in this case it's actually system identification. So let us say if we have, let us say, a large set of experimental measurements for like some known inputs, and we measure, let us say, the corresponding outputs, and then we basically try to fit a model, uh, or basically to find a model which actually fits this input output relation. So for that, let us say, where we let us say, for example, we have like measurements of temperature or pressure or something like, and the input variables, let us say, are, let us say, some kind of flow rate or something. Then we find out uh, what are the, like, let us say, for the state variables, let us say it may be some concentration of, or like, let us say, ratio of some two quantities which are, like, let us say, being mixed in a system. Then that for that, let us say, using that as a state variable, then we find out the corresponding model that relates these quantities. So that's what we call as generally system identification. So does that make sense?
Yeah, thank you very much for the clarification.
Okay. Okay. So yeah, so which of these examples, like, is it's like a discrete system in this case?
Yeah, in this case, the answer is number one, number of students running the
Yeah, number
class.
of students, yes. It's a discrete thing. Yeah. Yeah, so then, so like, can you give an example from day-to-day life in which where we need to apply both continuous and discrete event simulation methods to, let us say, analyze the behavior of a system? So can you think of an example, so where we have like both kind of things in the same system? So anyone has any idea what kind of example you can think of? So basically continuous and discrete event simulation. So they are basically two different kinds of methods. So one is where, so continuous simulation, so it generally involves like quantities which are like varying continuously with time in a continuous fashion, and discrete events like where you have uh, the quantity varies in a discrete manner. So like it has certain specific values which suddenly change with time. So let us say like uh, you can say like so yeah, if you are you able to think of any example?
See, related to discrete event, anything that we are doing on a daily basis. For example, as a teacher, we are going to college every day, or and then during the class for 1 hour we are taking the class. So I think it can be considered as a continuous for 1 hour, but
Hmm.
something like this.
Yeah, so like it's like over a week, so it will occur at discrete times, and like within that, whatever happens in that, let us say 1 hour duration, it's a continuous thing. Yeah, so that's also a good example. Any other like thing you are able to, anyone else wants to share any other example? So yeah, so I can give you one example for so consider like a ceiling fan, simple ceiling fan which we have it in India. You can commonly see it in most of the homes in India. So there you have a fan regulator which like at least in the earlier olden times you had like the fan regulator which operates at different discrete positions. So now once you change the, let us say, switch position, so then it actually changes the speed setting for that fan. So now once you basically keep changing the fan setting, so now the voltage is fixed, let us say in India, let us say 230-volt supply. Now the current drawn will change based on the speed setting. And now once you change the regulator position, the fan speed does not change immediately. It will take some time for the fan to respond to that. So there is some time for the taken by the fan to adjust its speed, let us say from one setting to the other setting. So you can basically consider that as the response between two different speed settings as a uh, basically like a continuous kind of event. And the when like during and there will be certain instances where you will be changing the speed setting, so you will be basically suddenly causing changes in the system by changing the fan regulator position. So that's a discrete event. So does that make sense?
Yeah, yeah, it's correct.
And also like now there will be now you would have also observed that the fan speed will vary during, also like even for the same speed setting, the fan speed actually will change throughout the day. Why do you think it actually changes? Anyone has anyone has observed this? So anyone has any idea why, like has anyone observed this and anyone knows why it happens? So you would have observed, like let us say for the same speed setting, the fan speed during the, let us say, daytime, and when you actually operate it at night time, so the fan speed is slightly higher for the same speed setting during the night time.
Yeah, it may be because during night the load is less, overall load, and the voltage may be a little bit higher
Yeah, yeah,
compared.
exactly. Exactly. Yeah, that's the precisely the reason. Basically, so when there is less demand from the electricity grid, so then you will get like higher speeds for the fan. So there are basically some voltage fluctuations, and so which cause that like slight changes in the speed. Yeah. So yeah, so another example which can think of is, let us say you are analyzing the behavior of a geared vehicle. So which has like let us say car which has like different gears. So there are like so when like let us say if you want to estimate the fuel consumption of that vehicle for a certain let us say given route, so the car travels at certain speed, and so now so there are some quantities which are actually changing in a continuous fashion. So the speed will be changing continuously, uh, the engine speed, the wheel speed, the torque acting at the wheel on the wheel. So those will be changing in a continuous fashion. But at certain instances of time, you will be actually uh, suddenly changing the gears. So those are discrete events. So you will be suddenly changing the gear number from 1 to 2, 2 to 3, or whatever. So during the while traveling in the route, so depending on the vehicle speed and road, uh, the road condition. So there you will basically you need to deal with both continuous as well as discrete quantities. So those are some examples which I could think of. So anyone was able to think of any other example? Yeah, so anyway, but so generally, like, is this discussion helping you to put the concepts in some perspective and like understand the application of it? Is this discussion helping you?
Yes,
Hmm,
yes.
yes, sir.
Yeah, so yeah, I just basically try to like visualize some common examples by which we can understand these terminologies. Yeah. So then this particular slide which I wanted to cover, so I thought that there is some analogy between some of the terminology that is used in this particular course and also in what we generally study in thermodynamics. So in this course we have like definitions like what is system and what is environment. So this and how do we separate the system from the environment and all those things. So in thermodynamics we have a similar kind of analogy for that. So we study what like we consider it like the universe in two parts, like what is system and whatever is outside the system is the surroundings, and what defines the separation between them is the boundary. So it's very similar to like the concept that has been covered in this course also. So I thought we can actually apply that same analogy to define and understand what they actually mean. So we have three different examples which are shown over here. So um, so depending on whether there is exchange of matter and energy between the system and surroundings, we can classify them into three types. So basically open system, closed system and isolated system. So whenever there is a exchange of both matter as well as energy with the surroundings, so that is called as open system. So we have an example of this, let us say some cooking pan or something which is placed on a cooking stove or something. So there, the cooking stove is providing heat or basically energy, and there is, let us say, food or water, something that is boiling in the cooking pan. So it is like exchanging like energy with the surroundings, and also like let us say water is getting evaporated. So some matter is like the water vapor is also leaving the cooking pan and entering into the air, atmosphere or whatever. So there is exchange of both energy as well as matter in this case. Now if we close the lid of that, let us say, cooking pan, So, and we do not allow any water vapor to escape from it. So then there is, like, let us say, no exchange of matter or negligible exchange of any matter, but energy is able to enter and exit from the system through, let us say, conduction. Uh, so the gas is like the cooking stove is basically providing heat to that. So energy is able to enter it, but so that is an example of closed system. And now we have the example of, let us say, the thermos flask, where there is it is tightly sealed and we do not allow any exchange of matter or energy. So that is an example of isolated system. So these are the same three kind of classification, which is the same terminology that we are coming across in this course, and it is the same thing which we would generally come across in thermodynamics. So I just wanted to uh, cover this so that so you would, I think, be able to apply that analogy similarly. So yeah, so next I wanted to discuss about this example about a hydroelectric power plant. Uh, so this picture which is shown over here, so it's actually from the slides itself. So so I just wanted to cover this, apply this concept which we just defined right now uh, to this particular example. So a hydroelectric power plant will have, like, we start with a water reservoir, and and then we have somewhere like a turbine which is able to generate electricity by converting mechanical energy into electrical energy in the turbine. And from that generator, so generator is basically generating the electrical power, and then that is transmitted to different locations. So it has different amount of, like, lot of energy conversions which involved in this. So I just wanted to cover uh, like different parts of this. So depending on so now we have this huge system, but depending on what we want to actually study in this, how do we select what we should include in the system? So let us say if our goal is to analyze the pressure distribution on the walls on the reservoir. So let us say if our objective is only to analyze that pressure distribution on the walls of the reservoir. So then what all things will we include in the system? So where do we put the boundary basically in this case? So any idea how we can do this?
I think it depends on the available water head.
Yeah.
It is and pressure distribution on the walls on the
Yes.
as well as on the drainage.
Yeah. So yeah, so you're right. So I was just asking basically where will you put the boundary in this case? Let us say if I were to select, which part, so there are like several parts which are shown in this picture over here. If I have to kind of draw a boundary, like only which is the only relevant so thing within this, like this whole thing, there is only some part which is relevant if I want to analyze, let us say, the pressure distribution on the walls of the reservoir, right? So so where will I put the boundary? So yeah, so I'll just say that I will put a boundary here. So whatever is inside this red colored box, so I will be interested only in that part when I want to analyze the pressure distribution on the walls of the reservoir. Why? Because uh, the pressure distribution, so first of all, why do we have a pressure distribution is because of the effect of gravity, pressure of the exerted on the walls of the reservoir varies with the depth. So, so as you can see that, the it's shown in the picture over here. So the thickness of that wall of the reservoir, it actually increases as we go deeper. Why is that? Because the lower sections of the reservoir walls have to actually withstand more and more pressure. So the pressure will actually increase linearly with the depth. So that's why the shape actually is like the thickness is kind of varying, increasing linearly with the depth. And so because there is a huge mass of water and it will be just some water will be leaving out of this conduit. So the flow rate, like the velocity of the fluid flowing out of that is like small as compared to the huge like mass of water that is here. So it's more or less like a static pressure distribution. So we will be basically be interested only in this what is happening inside this red colored boundary. So why is it like always choose important to choose where should we put the boundary is because we should select only that part which is relevant to what we are studying. So let us say we can apply this same analogy to any kind of problem that we have at hand. So depending on what our goal is, we have to select the boundary and select only use that part for our modeling purpose. So next, let us say if we have our goal is to analyze, let us say the energy losses in the fluid flow from the reservoir to turbine. So then where will we put the boundary now?
So we will keep the reservoir within our boundary.
Okay, and what else? Like like what all things will we include in that apart from that?
So that maybe we can consider a turbine also, because there will be when the water is used to rotate the turbine, so there will be some losses there also.
Yes, you're right. So yeah, so if we want to study, let us say, what are the energy losses in the fluid flow only from, let us say, the reservoir output up to the turbine input, then this is where we will put our boundary. Uh, so, so like if we are also interested in the energy losses inside the turbine, then we'll also have to include the turbine. But let us say if you are just interested in up to the input of the turbine, this is where we will put the boundary. So first of all, why will there be energy losses is because whenever a fluid flows through some enclosed channel, let us say this conduit and like this penstock and etc. So there will be because of the viscosity of the fluid, um, so there will be basically friction between the different layers of inside the fluid, and there will be as the water flows through these different pipes, etc. So there will be losses in the pressure head or basically the energy. So whatever pressure head is available at the reservoir because of the fluid flow, so there will be some losses as it reaches the input of the turbine. And further inside the turbine, because there are like several rotating parts and there is like, some undesired motion of the fluid which will, cause unnecessary some of the energy will be actually dissipated. So we basically have the conversion of potential energy of the fluid to kinetic energy just before the like as the fluid enters the turbine. And inside the turbine, this uh, kinetic energy of the fluid will cause the turbine blades to rotate, which will generate mechanical energy. So now inside the turbine again, we will have like, let us say, moving rotating parts, mechanical rotating parts. So there will be again friction, some rolling friction. So there will, although it will be having some bearings, but still there will be some losses because of friction. And also there will be some, also the conversion of the kinetic energy into like the mechanical energy or kinetic energy of the fluid into let us say the rotating like the rotating mechanical energy of the turbine shaft, or and then finally converting into electrical energy. That is also not 100% efficient. Yeah, so as you just described, so if our goal is to determine the mechanical power developed by the turbine for a given fluid flow rate. So then any idea which part will include?
So we will include the turbine in this case.
Yeah, so you're right. So you'll include the turbine, but also importantly, we will also include the this draft tube, tail race, etc. So because some fluid is actually entering the turbine and some fluid is leaving the turbine. So there is some kinetic energy of the fluid that is entering, and there is, let us say, some kinetic energy which is like very less as compared to the fluid entering, but there is still some, let us say, kinetic energy left in the fluid. So the water will flow out of the draft tube. So the change in that kinetic energy is basically the mechanical work that is being developed. So the mechanical power developed, or mechanical work that is being performed by the turbine. So for a given fluid flow rate. So that's where we will put our boundary in if our goal is that. So now next, if we want to determine what is the electrical power developed by the generator for a given mechanical power developed by the turbine. So now in that case, as I think it's easy to guess that we'll put the boundary just around the generator, because some mechanical power would be entering the, like, generator. So it will basically that's the input to the generator. So the rotating shaft of the turbine is attached like to the generator through some coupling. So that causes the generator to move, and because of the electromagnetic interactions within the generator, so there will be a electrical power. So mechanical energy is converted to electrical energy for a given, let us say, certain mechanical power developed by the turbine at certain speed. So depending on the speed of the turbine and uh, what is the power input, so we'll get the expected output of the generator. So again, that is also not 100% efficient. So there will be again some losses in that. So because of the inefficiency in the generator, so all those things will also cause some energy losses. So basically, depending on what is our goal, we will basically select only those parts of the system which is like, let us say, systems generally will be very big, they involve several things, but we only select that part which is relevant to us. Now if we want to develop model, like, for, like, let us say we want to find out what is the electrical power as a function of the given fluid flow rate into the turbine. Now we will include both the generator as well as the turbine together. So the input in this case would be the the fluid that is entering into the turbine, and then both the turbine and the generator combined together, we will basically get the output will be the electrical power. So for developing that kind of a model, we will basically putting our boundary like this way. So does it make sense?
Yeah, yeah,
Yes,
yeah.
sir.
It's fine.
Yeah. So it's basically the same two things, but when we want to now, depending on what is our input and output, we will select our boundary accordingly. I think next example is also simple. So if you want to determine the electrical power losses during transmission from the source up to the load, so then we will be just including the last part where we have the power from the generator coming in, and because of the transmission, so I square R losses. So basically, because of the current flowing through a conductor, so there will be always some electrical resistance for any given conductor, no matter what, unless it's like a superconductor, there will always be some losses because of the current flowing through any conductor which has some non-zero electrical resistance. So there will be losses. So if you want to study those, we will be selecting our boundary like this. Now, if we want to analyze, let us say, the variation in the electrical power available at the load and how it varies with the reservoir water level. Now, where will we select our boundary now?
Now the boundary will cover each and everything, starting from reservoir until a load center.
Exactly, exactly. So I think you now get, I think, the concept that depending on what is our input and output, we will actually include the different parts of the system which are relevant to us. So I just wanted to choose this example. With the same system, you can actually study the relevant parts and analyze what is required only. So yeah. So any questions or comments till now? So also just let me know whether you are able to uh, like follow, like am I going too fast or too slow? So just let me know. Is it okay? Like,
Yes, for me it's fine.
Yeah, it's okay, sir. It's good.
yeah, fine. Okay. So now, like in this week's content, we have like just the general introduction to like the terminology of modeling and simulation, and like we have not really gone into the specifics, but I just wanted to give you an example of selecting a particular example. Let us say damped free vibration for let us say a simple, let us say if we have a simple spring mass damper kind of a system, how do we basically develop the model step by step, and then how do we use uh, basically how do we derive the response of that system to different, let us say, input conditions. So and how do we use basically MATLAB as a tool to simulate this particular response. So I wanted to use this example to kind of illustrate that. So this is more or less of a demo. It's maybe not exactly like what is probably expected in this course. So, but I think it will be helpful for you to understand how you can use MATLAB as a tool and what are its like functionalities, general functionalities. So shall we go through this example?
Yes, sir.
Yeah.
Yeah, yes.
Yes, yes. So this is something that I think most of us will be familiar. Like I think mechanical engineering people will definitely be familiar with this, but for like people who are from other backgrounds, they will have like they would have encountered this thing at least in I think 11th standard, 12th standard physics or something like that. Or in mathematics also we come across this particular example for in especially in the when we are studying about differential equations and all. So yeah, so in this case, let us say this we have a simple spring mass damper kind of a system. So in reality, we never have a system which actually looks like this, but this is again a model of some certain system. Like let us say if we have a machine which is mounted on certain foundation, so it can actually be represented in like by this model. So it is actually a lumped, what is called as a lumped parameter model. So any mechanical system as such can be thought of having these three, let us say largely these three properties. It will have mass, it will have some stiffness because of the the elasticity of the material with well, because of which the like it is made of like different materials. So there is no rigid material in reality, so it will always have some elasticity. So whenever it is subject to some force, there will be some deformation, so it will always have some stiffness, basically stiffness, or in other words it can also have some compliance. So compliance is like the inverse of stiffness. And because of the the different like molecular interactions and because of viscosity and all those different effects, there will be always some kind of a resistance to some like motion. So whenever like let us say if you see like a pendulum, for example, so whenever a pendulum is swinging in air, it will always tend to slow down and after some time it will just come to rest because of the damping present in the system. So damping is some it can be because of like let us say air resistance or because of the viscous drag or different kinds of forces which basically resist the motion. So we'll represent it by the parameter called as damping. Now whether that is viscous damping or other kind of damping like Coulomb damping because of let us say the Coulomb, what is called as Coulomb friction, which is let us say because of rubbing of two different surfaces, that will also cause some friction. Viscous friction is basically when we have interaction between the surface and the fluid. So this is like a model where we kind of which is called as lumped parameter model, as I said. So it will represent it as a mass, spring mass and damper system. We can actually use this kind of a model and apply it for like different kinds of systems. So one is example as I gave, like machine mounted on some foundation, or let us say even if a car is going on a road, so the suspension has some stiffness and also has some inherent damping characteristic there. So the we can lump the entire mass of that car like and represent it as just a block of mass. So this is like a very simplified representation, but we can extract like some to some extent we can like at a gross level we can analyze what will be the behavior of those kind of systems either using this lumped parameter model. Now if we want to now analyze like let us say the motion of let us say this system uh, when we apply let us say some like if the mass is moving and like let us say the displacement of that mass, let us say from its equilibrium position O is some x uh, in the downward direction. So now what would be the forces acting on that mass? So it will be basically the force because of the spring, and the other force because of the damping. So the spring force is generally represented by K into X. So K is, so when we have a linear spring, so where the force acting like force acting on the mass because of that spring is like proportional to the displacement, so then we call it as a linear spring. We can also have a non-linear spring where, so the force acting because of the spring can actually be also K into X square, or any some K into X to the power something. So that will be a non-linear spring. But let us say if we have, for the in the simple case, let us say we have a linear spring, then we can call it the spring force as K into X. So yeah, and then in case of damping, so generally the viscous damping is proportional to the relative velocity. So now in this case, so we are showing this as a damper with one end is actually fixed to the wall and the other end is actually moving. So the other end is attached to this mass. So the relative velocity is x dot, or because the other end is actually fixed. So the relative velocity between the two ends of the damper. So it's, so the damper symbol is actually like a piston cylinder. So where there is a relative velocity between the piston and the cylinder. So it's not necessary that always one of them should be at rest. The other both can actually be moving. What matters is the relative velocity. So the force actually depends on the relative velocity between the piston and the cylinder. So that's what we call as C into X dot. So again, this is another kind of a damping model which we call as viscous damping model. So where we represent the force because of damping, viscous damping, as proportional to the relative velocity with, so the C is called as the coefficient of damping. So this is another simplified model of damping. So in reality we may not really so in reality we will be having all other complicating effects. So in reality there will be always different kinds of friction present in combination. So like, combination of viscous friction as well as uh, Coulomb friction. So the piston is actually rubbing against the wall of the cylinder. So there is also Coulomb friction present, but let us say the damping force is causing, like, which is caused because of the so in a piston cylinder, why do we have like damping caused is because of the fluid passing through, let us say, some orifice. Let us say the piston has some holes, and the oil is basically made forced, like, forced to pass through that holes in the orifice. So that causes the energy losses, which slows down that system. And so that's how we can actually, so in reality the construction of dampers is much more complex, but we can kind of simplify it and represent it as, the damping force is some C into X dot. So this is basically the free body diagram which is shown over here. Now, why am I explaining all this thing in very detail, like in detail? So I think the mathematical derivation part, I think all of you must be very much familiar, but I think, uh, you know, many people may not be actually aware that, this is a simplified representation of a large class of things, uh, which can actually be applied to different contexts. So that's why I actually wanted to give this context also. So now once we have this free body diagram, so we have not shown the weight as a force in this free body diagram over here. So anyone has any idea why do we don't do that? So yeah, so I'll just tell you why. It's basically when we uh, so in reality the weight is actually acting, but it is not varying changing with time. So now here we are measuring the displacement with respect to its equilibrium position. So x is the deflection from its equilibrium position. So there is some static deflection from the free length of the spring. Uh, so the weight of the mass is being balanced by the static deflection of the spring, and what we are actually measuring is the change with respect to its equilibrium position. So the k into basically the static deflection and the weight, which is m into g, are always in balance, and whatever additional deflection that we have, so that is kx, which is the unbalanced force. So the total deflection of the spring is basically k into x plus some static deflection, but that static k into static deflection is being balanced by that mass into m into g. So that's why we are actually cancelling it will be cancelled out, so then we don't show the force like that. So now let us say we are subjecting this system to some initial conditions. So we give, let us say, some initial displacement at time t equal to 0, which is, let us say, some x naught, and some initial velocity which is called x naught dot. So was someone trying to join? Okay. So now, so can someone tell me like what is the next step if we want to like analyze the response, like basically the how the displacement velocity vary with time for the mass. What is the next step that we apply?
Now we will solve these differential equations.
Yeah, so before we even solve the differential equation, we first have to derive the differential equation.
Okay, yes, yes. Okay.
Yeah, so to derive the differential equation, so in this case it's a simple mechanical system, so we can just simply apply Newton's second law. So mass into acceleration is the sum of the external unbalanced forces. So the external unbalanced forces in this case for this mass are just the spring force and damping force. So m into x double dot is so let us say the acceleration is like in downward direction, and the forces are actually opposite to the acceleration, which is kx plus cx dot. So it's basically we'll get the differential equation of this form. So mx double dot plus cx dot plus kx is equal to 0. So I think all of you would be familiar with this kind of a differential equation.
Yes.
Yeah, so how do we solve this differential equation?
To solve this differential equation, we can use classical calculus method, or we can apply Laplace transform, and then we can solve.
You're right, yes. Yeah, so it's basically a second order linear differential equation, or like ordinary differential equation with constant coefficients. So then in this we can actually assume a solution of the form x is c e to the power st, and then we substitute this solution in the differential equation. So we will basically differentiate this twice, and like so, and substitute it, like differentiate and substitute it, and so we'll basically get a characteristic equation which is ms square plus cs plus k equal to 0. Why? Because e to the power st is not 0 for any real value of t. So therefore the coefficients should add up to actually 0. So I think most of you would be familiar with this process, and now it's actually just a simple quadratic equation in S. So it's basically the exponent e to the power st. So that S we can solve for in terms of the mass, stiffness, and damping characteristics. So if the values of mass, stiffness, and damping are such that the equation has, let us say, two real roots, then this is the usual formula to solve the quadratic equation, and these are the basically two roots. So if it has two real roots now, so then we can write the general solution as the combination of the solution, like with, like, let us say the root s1. So we call root s1 with, let us say, with the positive sign, and the s2 with, let us say, the negative sign in between. So we have this plus or minus here sign here. So those two real roots, so we can for those two real roots we can write the general solution in this way, with coefficients c1 and c2, which are basically the weightages of the two distinct solutions that we have. Now, how do we calculate the values of C1 and C2?
The constant C1 and C2 are calculated based on initial values.
Exactly, yes, you're right. So we substitute the initial conditions and then find out what is C1 and C2. But this is valid only if we have two real roots. So now we will be having cases where we may not have real roots. So let us say we have depending on the nature of the roots, we categorize them into three parts. So first case is called as underdamped case, where we have the value of this c by 2m. C by 2m is actually uh, less than c by 2m is less than root k by m. So in that case, we will be getting the thing which is inside the bracket, square root, as negative. So then if we apply the same formula for calculating the two distinct real roots, so we will actually find out that this term which is inside the square root is actually imaginary. So root of, it's negative, so root of square root of a negative number, it is imaginary. So then we write the solution in this form. So we actually define a parameter called as, let us say, zeta, which is c over cc, which is the critical damping. So that is the called as damping ratio. So we basically just, it's kind of a substitution to make it more simpler to mathematically simpler to deal with. So when this damping ratio is less than 1, so it's called as underdamped. So then we'll have two complex roots, so which will have real part and the imaginary part. So then we can write the general solution in that same way, c1 e to the power s1t plus c2 e to the power s2t, and then we can find out the coefficients c1 and c2 by substituting the initial conditions. So now here the nature of the roots is slightly different, because the roots are complex, then we can use that property that e to the power some complex, so e to the power I omega t is cos omega t plus I sin omega t. So using that property, which is called as de Moivre's theorem or something, so that using that we can basically write e to the power I omega t as that cos omega t plus I sin omega t for both the parts of this general solution. So which will be so now then by rearranging those terms, we will get like two different constants now, which is c1 prime and c2 prime, which are constants like coefficients of cos omega t and sine omega t or whatever. So those will again we will be able to find out from the initial conditions. So we will get the so I'll be not going through the derivation. It's just basically like I'm just going through the derivation. I think most of you would be familiar. So you will actually be finding this in any textbook on vibrations. So for example, SS Rao or something. So the specific expressions you will get depending on the initial conditions that you apply. The second case that we would get when we have two equal roots of S1 and S2. So that will be the case when C by 2m is exactly equal to root k by m. So then we can write now the general solution in this form, C1 plus C2t into the e to the power minus omega n t. So omega n is the natural undamped natural frequency. And now by applying the initial conditions, we will get the values of C1 and C2. So this is the critically damped case where the damping ratio is exactly equal to 1. And then we again will have a third case where it is called as over damped. So there the damping ratio is greater than 1. So the term inside the square root will be positive. So in the critically damped case, the term which is inside the the square root is 0. So then we'll have two equal roots. In the underdamped case, we will have two complex roots, and in critically damped we will have equal roots, and in overdamped case we will have two distinct real roots. So those will be the coefficients of e to the power st. So we will write the general solution in that same way and apply the initial conditions to get the values of C1 and C2. Now if we want to compare how these the response looks like for the different cases and for different initial conditions. So this is the graph that you would find. So in the undamped case, the amplitude of the oscillations, basically the uh, x varies with time, basically like a sinusoidal. It has a sinusoidal nature, or basically it's like a sine wave kind of a nature, which is shifted in time because of the phase difference. So it's like a so the sine wave starts at some non-zero value x naught, and starts with some non-zero slope. So so it is basically some sine omega t plus phi kind of a function. So where phi is the phase difference, so it's a sine wave shifted in time. And we have the next case where we have the underdamped case where there will be oscillations, but the amplitude of oscillations will be decaying with time. So where the damped natural frequency is actually slightly lesser than the undamped natural frequency, but there will be oscillations with that frequency till the time where the amplitude actually becomes so less that it's like almost at rest. Now in case of the critically damped and overdamped case, you can see that there is no oscillatory kind of a nature. It just starts with some initial velocity, goes to a maximum displacement, and then just drops down without oscillating and settles down to asymptotically it converges towards 0. So that is called the critically damped and overdamped cases where there are no oscillations. So the nature of the response actually changes depending on what is the mass, stiffness, and damping characteristics. So now let us go to MATLAB now. So where I actually have written. So is everyone able to see the MATLAB window?
Yes, sir.
Yeah. So here
Yeah,
I
yes.
actually Yeah, so this is basically the MATLAB window. So yeah, so this is like, let us say, the command window which you have, and here you will be having the workspace. So the workspace, what's the workspace? It's basically, it shows like which are the variables that are currently, like, let us say if you run a certain program, uh, so which are the particular variables involved in that program, and what are its values. So the workspace actually shows the name and value of those. It also shows the data type, whether it's a integer value or string value or whatever. And here it shows basically the on the left hand side, extreme left hand side, it shows the, the current folder in which we are present and what are the different files that are present in this folder. So you can set the working directory here, that's called a working directory. So you can browse to whichever folder that you want, and navigate it to the particular folder in which you want to work. And let us say if you already have some MATLAB files created, or you want to have the MATLAB files created in a particular folder, so you can navigate MATLAB to that particular uh, path where you want the folder, like navigate to that particular folder where you want to store them. So there is something called as the current working directory, and then there is a MATLAB path also. So what is MATLAB path? So when you give some command, or let us say if you let us say if I want to run a certain MATLAB file or MATLAB code which is present in some folder, but so then what MATLAB does is that when you try to run that, so it actually searches for it within the MATLAB path. So if it is present in the current working directory, so it will be able to find it. But if it is like some file which is in some other folder which is not the current working directory, and still you want to run that code, let us say if it is in some other folder. So let us say if I have, like, this folder, and there is some file which is outside this folder which is shown as like week 1 over here. So um, so then what will happen is that if there is some MATLAB code outside that folder, and if it is not added to the MATLAB path, then MATLAB will not be able to find it. So you can also set the MATLAB path. Uh, so let us say if I want to set this, so like let us say if I have like multiple MATLAB files which are present inside like the folder, not necessary to the particular current working directory. So then what you can do is, like, you can say like right click and say add to path, and say selected folders and subfolders, so uh, which will enable MATLAB to find whatever files which are contained within that folder and the subfolders within that. So that's how you can set the MATLAB path. Now, and so I have a different editor, MATLAB editor window, where I am writing a MATLAB script or MATLAB code. So you can basically, so code, MATLAB code is basically just a set of instructions given to the computer to do different tasks. So you can also write the code directly into the command window, but it's also possible to execute the code directly by typing it into the command window. Let us say some x is equal to something 1. So you will be able to see this in the workspace, so that value of x has been assigned to, like, the value of 1 has been assigned to the variable x. So you'll be able to see it in the workspace. And let us say if you want to suppress the output of the, you want to assign, let us say, the value of 2 to x, then but suppress the output. So you will be able to see that the value of x has changed to now 2, and with the semicolon, you will be able to suppress the output. So there is no display in the command window. But now, so let us say you are having some multiple lines of code which you want to execute step by step, and you want to reuse that. So then for that, you will be creating a new MATLAB script and then type the, let us say I select a new uh, MATLAB script using this. So now I'm using MATLAB version 2020A. So you maybe if you will be using some other version, the menu will be more or less similar. So for most of the functions. So here you can basically have a blank MATLAB script, and then you can type whatever the code. Let us say you want to reuse y equal to something 2, and let us say you want to calculate z is equal to some x plus y. So you can also copy this code and paste it in the command window. So again, it will be executed. So z is equal to x plus y, which is 2 plus 1 plus 2, which is 3. And if you want to run this MATLAB script, so I'll name it first. You will have to save the MATLAB script by some file, give it some file name, and it will be saved as a .m file. Let us say I call it as test. And to run this MATLAB script, so I have to press this run button. So before that, so to just check whether I'll be getting the same output, we will first clear the workspace. And if you want to clear what is there in the command window, you can type the command clc. So it will erase whatever is present on the command window. You will return to the first line. And if you want to clear the workspace, clear all the variables from the workspace, you can say clear all. So that will erase all the variables in the workspace. Now we will again go to our MATLAB code and say run, and then we will see that the same variables have been created in the workspace. So x, y, and z with the expected values. So this is how you can create a MATLAB code and run it using MATLAB script. So it's better to always use a MATLAB script so that you can keep reusing the code and make changes and rerun it, as compared to directly using it, typing it in the command window. So now again we will do clear all and CLC to clear our command window and workspace. So now here I already have a code which is written for this particular example where we have this spring mass damper kind of a system. So here what we are doing is, in this code we are trying to analyze the response of the system to different initial conditions. So in MATLAB, so here starting from line 4, so here as I said, the first line is basically adding a particular folder uh, to the MATLAB path. So by using the add path function, so I have let us say some file called as set graphics, which sets the properties which I want, desired properties of, let us say, what is the desired line width and the font for the figures that we generate. So if you don't do these settings, MATLAB will use its default settings for the figures. But if you want to use a customized setting for the figures that it will generate, you can write another piece of code and you keep reusing it as per requirement. So the first two lines are for that. Now the beginning from line 4, we are actually starting with the actual MATLAB code now. So any questions or comments till now? Like, are you able to follow what all I am saying?
Yes, I am fine with this.
Yeah, about what about the others? Like, are you able to follow?
Yes, yes.
Okay. Fine. So we are actually now trying to code this particular example into MATLAB. So we define what so here now because of the simple differential equation that we had for the single spring mass system, we were able to actually find out a analytical solution for this because the differential equation was simple for that problem. So then here we are actually trying to find out what would be the response for different sets of these parameters, like let us say mass, damping and stiffness. So now instead of using some symbolic values of K, C and M, we will actually define some particular values for the mass, damping and stiffness in MATLAB, and then try to plot the how the response would be for those set of parameters of mass, stiffness and damping, and for the certain set of initial conditions. So basically these are the set of parameters. So and now depending on the values of these parameters, what will actually change is the damping coefficient or damping ratio, whatever like the so damping coefficient or damping ratio. So you would have observed that there are some lines which are written which look green in color. So those are called as comments. So whatever is text which is written after typing percentage, so that is called as, so MATLAB will understand that this is a comment. So MATLAB will not execute those lines of code which are after this. So whatever text that comes after this percentage symbol, MATLAB will not run that, not execute that. These comments are useful for our own understanding, uh, to basically understand what exactly this every line is doing or so. So here, so the first line is like, line number 5 is we define the mass in kg. In the second, like next one, we define the damping value in Newton second per meter, the damping factor, and then the stiffness in Newton per meter is defined as K. So then the undamped natural frequency omega n we are calculating here as square root of K by M, and here we define the initial condition. So the so here if I type percentage twice, it actually generates like a section within the code. So this actually helps in visualization of the code. So it's basically facilitates easy understanding. So this section is basically initial conditions, and here we define the time interval for the response at which. So whenever we are doing any computer simulation, we are doing it for a particular time interval. So all like so in other like apart from the analytical solutions, so which is like a general solution which is valid for any time interval. So for a computer simulation, we give it a particular time interval for it to analyze. So this is like, let us say here we basically create a time array which is time from like let us say 0 to 10 seconds here with steps of 0.01 seconds. So this is how this is the command which creates this time array directly for us. So we don't have to actually list down the values manually. It actually this command so 0 colon step and the So start time step and start time colon time step colon end time. So that creates this array for us. So now the other parameter which we have is the damping coefficient zeta or the damping ratio. So this is again another model parameter itself. So we'll actually transfer it to the parameters section. So these are so for any given set of parameters and any given set of initial conditions and for a given time interval. So these are the three major inputs to this code. And now we come to the part where we actually check whether in which category of the response we will get. So whether the system is under damped or in the over damped regime or critically damped. So depending on the set of stiffness, mass and damping. So c square minus 4mk. So which is the thing which actually comes under the square root in our the solution. So depending on the value of that, whether it is positive or negative or zero, we will get the uh, particular response for that particular condition. So here I have created a if else kind of a structure. So here like if the first if it checks whether first this statement is true. So if it is true, then it will execute whatever is after this if statement. So it will display in the command window whether it is under damped or over damped or critically damped, and then calculate the required quantities, which is like, let us say in case of the under damped, it is the damped natural frequency, and the next one is basically the particular expression for the uh, what is the response, like the expression of the response that we derived from our analytical solution for that particular case. So this now if the this statement was not true, then it will go to the next statement. So it will again check whether it will go to the else if case. So where it will check for the other case where it is like the c square minus 4mk is positive, then it will calculate the response as per the over damped case. So this is like the same I have basically used the same uh, values of the like the expressions for the solution which we had from the derivation. So I've just directly used those, and the values of the coefficients, so you can calculate them by applying the initial conditions. So you can actually derive the expressions for those unknown constants c1 and c2 in terms of these parameters and the initial conditions. So this is the response for the overdamped case. And then if the both of the above statements are not true, so if it is neither negative nor positive, and then it will be actually zero. So in that is the critically damped case, so which is line number 29. So the else part will be executed, so then it will be saying it is critically damped, and then calculate the solution for that case. So this is how we can create the if else kind of a structure to um, check whether in which regime like the response will be in whether of what category, and calculate the response for that particular case for those set of parameters and initial conditions. And then we come to the next figure, line number 34. So we will plot the response with time. So we give a figure command which will generate a new figure window, and then we use the plot command to generate a of plot of basically the. Uh, response x with respect to time t. and then we give the axis labels using these commands x label and y label. So let us now try to run this code. So let us say if we choose the mass as 1 kg and the stiffness is, let us say, 100 Newton per meter. So then the undamped natural frequency will be root k by m, which will be equal to 10. So so we know from like analytically that 2 into square root of k into m is the critical damping value, which for these value, like choices of k and m, we will get actually the value of 20 as our critical damping value. So let us first try to simulate for the case where the damping value is less than 20, which is the critical damping value. So I have changed the value of C now to 5, mass is 1 and K is 100. So I will just run the code and see how the response looks. So yeah, so this is the plot of the response x with respect to time. So we are simulating for 10 seconds, but we can see that the oscillations are actually dying down in just 2 seconds. So this is the very similar to the what we expect in the underdamped case. Now to check whether the plot is correct, so we'll check what will be the value of the damping ratio zeta. So it is 0.25, so it is less than 1, so it is correctly showing it as, so you can see in the command window it is printing as underdamped, which is correct because our original damping value is 5, which is less than 20, so it falls under the underdamped category. Now if we want, let us first let us try to decrease the damping even further and see how the response changes. We will just run again. So now we can see that because of the reduced damping, we can now see much more oscillations in the same amount of time. So let us compare these two figures. So this was the figure for the earlier value of damping, which was 5. Now this is for 1. So the oscillations are dying down with time, but uh, because of the reduced damping, we can see that the system takes much more time to uh, come to the equilibrium position of 0. Now let us increase our damping value to, let us say, 30, which is more than 20, which will be now greater than 20. So we will expect this to be over damped, so we should not see any oscillations now. So yeah, you can see that here the amplitude just increases. So our initial condition was that we are giving an initial displacement of 0.1 and initial velocity of 1 meter per second. So we will see basically the slope and the initial condition as per that whatever we supply. So here we can see that there is no oscillation and the x is just exponentially decreasing to 0 very rapidly. So this is the exactly what we expect for the overdamped case, and we can see that the code is able to correctly identify it as overdamped. So if we check the damping ratio, it is 1.5, which is greater than 1, which is the particular case as per the, when it is greater than 1, it is called as overdamped. And then let us come to the third case where we substitute the uh, value of C to be exactly 20 and then again run the code. So we will again see a similar kind of a response which does not involve any oscillations, and it rapidly just converges to 0. So this is how you can use MATLAB to uh, analyze the behavior of the system. So in this case, we had the like analytical solution. So you can also use MATLAB to get the system response where we do not have a exact analytical solution for the differential equation. So we'll look at those kind of cases subsequently as we go through the course. So any doubts, any questions, comments on this part?
For me, thank you very much. It is very nice and everything is clear.
Okay. Yeah, so you can create like a code like this to kind of explain these concepts to students also. It will be nice. Like you can create plots as per like you can also further improve these plots and all like as per our requirement. But yeah, so I have not gone through the all the specifics of the other the solutions how we derive those, but I think you would be able to understand it from any basic textbook on vibrations. This was just a demo to show you the how you can use MATLAB. So yeah, so that was about the example on MATLAB. So I had another demo. So if I can just take 5 more minutes, is that okay? So I can just
Yeah,
show
please
another
carry on.
demo. Yeah, I'll just quickly show another demo. Uh, I think you must be familiar with this part like logarithmic decrement, and so I'll just skip those. Um, yeah, in this question, sir, like so we have the statement. So as we understand, like analytical methods give a general solution, and simulation methods give a specific solution. So this is just exactly what we saw in the demo. So we derived the general solution from basic physics principles for that spring mass system, which is a general solution which is applicable for any case, for any set of values of the parameters. Whereas in simulation methods we have to give a certain specific set of parameters and the specific initial conditions to get a specific solution. So that's the generally what we have in computer simulations. So now I just wanted to show you another example where how we create a model for a car which is traveling on a bumpy road. So, so maybe I will not go into the details of the entire modeling and derivation of that. So I'll just quickly show you what are the capabilities of MATLAB that you can use to illustrate this example. So it's basically so you can again model the car like a simple spring mass damper kind of a system, and the wheel is like so you will assume that the wheel is always remaining in contact with the road. So you can represent the road surface like as the the road bumpy road as some profile which basically gives the variation of the height of the road from some reference with distance or time or whatever. So the car is moving at some velocity v. So then on which part of the road the tire is coming into contact with, and then uh, so you define basically the uh, x of t as the vertical up and down movement of the car body. You call it as let us say x, and the extent by which the wheels are moving up and down, that you can call it as let us say y of t. And because of the presence of suspension, which is like the spring and damper which is shown over here, because of the suspension we will feel less jerks as compared to if it was just a rigid thing going over the road. So I basically tried to select a certain representative set of parameters to for a passenger car, uh, So here it's again a lumped parameter model where we model like, the car body as some mass m1, the wheels together are lumped together as 100 kg mass, and we select the some reasonable values of stiffness and damping parameters, and try to simulate this model using MATLAB. So what we would expect is that even though the car is traveling on a bumpy road, the movement of the mass m1 should be as, the up and down movement of the mass m1 should be actually as less as possible to ensure passenger comfort. So that would be our design objective. If you want to design a particular suspension, we would like to have the value of y1 as less as possible. Uh, so uh, so we can see like a demo video. So I created an animation, so where I have modeled the road profile as some sinusoidal, up and down kind of a function. And so let us see how the masses move. So if you observe carefully, you would have noticed that the lower mass, which represents the wheels, is moving much more like up and down as compared to the upper mass, which is representing the car body. So we are able to successfully achieve our design objective, which is having the movement of the car body as less as possible as compared to the bump. So the amplitude of the road bumps is actually much more as compared to how much the extent by which the upper mass is moving up and down. So this is like a animation that you can create in MATLAB. So this was just to kind of illustrate uh, how you can use MATLAB to solve different kind of problems and also create animations and create graphs. So I also had a graph which shows like this same thing, like the mass m1 is basically the car body and mass m2 is like the wheels, which represents the wheels. So you can see that the orange or red or whatever that curve is fluctuating much more and with much more amplitude as compared to the blue curve, which is representing the car body, which is our expected output. So this is another demo which I wanted to show. So you need not really, this is not part of the course as such, but this is just an additional demo which I wanted to give from my side to show you how you can use the functionalities of MATLAB. So I hope it makes sense and hope it helps you and motivates you further, I think, to explore more features of these tools. So any questions, comments, or doubts?
Thank you very much. It is very wonderful, and
Yeah,
I
yeah,
hope
thank you.
that we will learn more by using your examples, whatever you have shown. And
Sure, sure.
this animation is really very good.
Yeah, sure. Thanks. So yeah, I think then that's all that I have wanted to share for today. So we'll be meeting next week in the next week's online session. So till then, I think you can. So I'll be sharing the recording as well as the lecture slides, so you can try out these things on your own in MATLAB. So yeah, so that's all that had for from my side. Thank you.
Okay, thank you.
Thank you very much.
Yeah, thank you. Yeah, thanks for joining. Good night.